Good afternoon, everyone. Welcome to the first parallel session. This is the algorithm 1 session. So if you can, please consider sit in the middle portion of the seats, the middle 3 in particular. Please consider to move. Okay, thank you very much for your cooperation. So it's my great pleasure to introduce our first speaker, Sevag Gharibian. He will talk about beating the natural Grover bounds for low energy estimation and state preparation. So the floor is yours, please.
Great, so you guys hear me? Good, super. Feel like a rock star coming up that stage. So this is joint work with Buhrman, Zeph Landau, François Gall, Norbert Schuch, Suguru Tamaki. My name is Sevag Gharibian. Most people just call me Zeph. So let's begin. Okay, so we all know and hopefully love Grover search, right? Which tells us that we can find a marked element in a search space of size n in time square root of n. Right, so the main theme of this work is, can we beat Grover search when it comes to ground state energy estimation? And the answer, as we'll see, as the Germans like to say, is jein, right? Meaning ja und nein, or yes and no. And hopefully in the next 20 minutes, I'll give you a sense of why the answer seems to be so subtle. Okay? Good, so let me start by defining the problems, of course. Okay, we're going to study two problems. The first is ground state energy estimation. I'll just call that LH. And here the input is a k local Hamiltonian. It's on n qubits. I want to be very clear. In this talk, by local Hamiltonian, we mean any local Hamiltonian. I make no assumptions about the geometry of the interactions or the type of interactions. Okay, it just has to be k-body interaction terms. And the input is some precision parameter, let's say epsilon. It's typically at least inverse polynomial in this setting. Okay, and the goal is to estimate the ground state energy to within plus or minus this epsilon. So this problem has long been known to be QMA hard, and it's even hard if we restrict it to, say, a 2D square lattice. Okay, this is a case I'll come back to later. The second problem we'll study is related. Now I don't want the ground state energy, but I actually want that low energy state. Okay, so it's defined the same way, but the output is a quantum state, and the energy of this state is supposed to be within the same energy bounds. Okay, and let me briefly point out that this problem is actually harder than ground state energy estimation. Okay, complexity theoretically, it's p to the QMA log hard, which means, and this class contains both QMA and co-QMA. So it's really a harder type of problem. But I won't say more about that in this talk. Good, so these are the problems we have. They're hard problems, so now we have to, ready our tools, right? So this is a cat, and you might think that this cat is relaxing, but I'm told it's actually scratching its claw. It's like sharpening its claws, right? So that's what we're going to do. We're going to get ready for attack. What approaches do we have to solve these hard problems? Okay? So in computer science, we have three main approaches. I'll just talk about two of them. The first one is exact algorithms, right? This is exactly the way I phrased the problem earlier. And of course, here we don't expect polytime algorithms for ground state energy estimation because it's QMA hard. Okay. But you might say, look, maybe I'll hope for something a bit worse than polynomial, maybe quasi-polynomial. Okay? And that's also ruled out by something called the exponential time hypothesis. This has been around for over 20 years now. It's been quite influential. And this, roughly speaking, says that we don't expect sub-exponential time algorithms, even for satisfiability, never mind for things like local Hamiltonian problem. Okay, but this is all classical. You might say, look, we've got Grover, we're quantum, right? And indeed, you can apply quantum. You'll get that, the natural Grover bound, I'll call it, 2 to the n over 2. Okay? And you might ask if we can do better. And, well, there's a quantum version of this ETH. It's called the quantum strong ETH. And this also roughly says that Grover search is going to be optimal. Right? You're not going to do better than that n over 2 in the exponent. Okay, so in particular, if you can see my mouse, like this C is more or less going to be a 1. Okay, so this basically says that if I'm trying to solve the exact problem in the absolute worst, most general case, let me be very clear. In this talk, I'm talking about worst case complexity. I make 0 assumptions about your Hamiltonian, and I want to solve every instance of this problem. Okay, so this is not happening in the exact setting, though, due to all these reasons. So this is not where we're going to go fishing. So instead, we'll turn to the second thing computer scientists like to do, which is we study approximation algorithms. And the definition here is similar. It's just that now I'm allowed to make a bigger error. Okay? And in particular, my error is allowed to scale with the system size. So m here is, think of it as the total number of interactions, if you will, in your system, or if they're weighted, the total strength of all these. I'll define these formally in a second. So you might think that this is a weaker notion of solving the problem. This is probably going to be easy now, but in general it's not, right? Because we already know the classical PCP theorem tells us that we can't hope to get efficient approximations for any epsilon I like, for example, for 3-sat. Okay, so poly times algorithms, again, are out the window. And again, you might ask for maybe a sub-exponential time algorithm, but in the last 10 years or so, there's been this gap ETH that's been proposed and used. And if you believe this hypothesis, it would say that at least there's some epsilon precision parameter over here, so that you cannot solve the problem to within this precision parameter in sub-exponential time. Okay? And that's kind of where my background will end. So the motivating question for this work, therefore, is that I want a really general algorithm. Okay, I want it to work for any epsilon. You tell me the precision you want, and I will come up with an algorithm that will hopefully run in 2 to the cn time for c smaller than 1. Sorry, 2 to the cn over 2. Yep. And so the question is, what's the best constant c we can get in this exponent? Okay, so now I can state our results. So let me be clear. K local Hamiltonian, n is the number of qubits. M here is the total sum over all interaction weights. And the first result we have is that there exists a quantum algorithm which for any k local Hamiltonian, again, let me be clear, I make no assumptions, for any precision parameter epsilon, outputs an estimate to the ground state energy to within plus or minus epsilon m over here. And this is the runtime. And the main thing you should focus on here is that this constant here is smaller than 1. Okay, so think of epsilon as k and k as constants. Okay, so some quick remarks. So first, this breaks the so-called natural Grover bound, quote unquote, and I put that in quotes for reasons that will become clear in a second. But what I mean by that, it breaks, a priori, this problem seems to have no structure. You would expect the best thing you can do is apply Grover, get that square root speed up, but no, it seems like we can do better. Okay? Number 2, another positive is that this is a rigorous worst case performance guarantee. It is not a heuristic. On the downside, the improvement is only asymptotically optimal, asymptotically small, right? So for example, for that 3-sat example I showed you with PCP, if k equals 3, if epsilon is 1 over 8, then we barely beat this like n over 2 runtime with 0.96 times n over 2. Okay, so this is our first theorem. It's about approximating ground state energies. I also talked about preparing low energy states. And so we have a very similar theorem here. And this one says that there exists a quantum algorithm, again, for any k local Hamiltonian and any precision parameter epsilon, now actually produces the state rho with this type of energy. Okay, and the runtime is almost the same. I just have this 2k in the bottom instead of just k. And this is because we're going to use the quantum singular value transform. We'll have to choose a polynomial to model some cutoff function, and there's going to be some loss there. So these are our 2 main results. Now, there are a few small corollaries I do want to mention. The first of these is perhaps a bit surprising. Personally, I view this as maybe the most interesting part of this work. This one says that for any k local Hamiltonian H, the number of eigenstates within this energy bound is exponential. Okay, so it scales roughly like 2 to the epsilon n. Okay? Now, this is a bit surprising, right? You might expect this for Hamiltonians which are geometrically local. But in our setting, we consider any Hamiltonian. Even all-to-all interactions are allowed. Okay? Now, for those of you, of course, with a quantum algorithms background, you've played with Grover search before, you like Grover search, right? Now your spidey sense might start tingling, right? You might say, hold on. So first, Zeph lied to us on the first slide when he said that Grover runs in square root n time, because we all know that Grover does not run in square root n time. It runs in square root n over m time, right? Where m is the number of solutions. And now Zeph is telling us that, at the top of the slide, the number of solutions is actually very big, right? It's exponential. So does this mean that for ground state energy estimation, even Grover beats Grover? And essentially, the answer is yes, right? The point is that what's surprising here is that even though the problem appears to have no structure a priori, right? It turns out that there's a very large degenerate subspace which has this type of energy bound. So if you were to even run Grover, you'd beat that natural n over 2 bound. Okay? But let me be clear, we don't use Grover in our algorithm. This is not how we came at it. This was a consequence of how we designed our algorithm, and the algorithm itself is very simple, as you'll see in a second. Okay, so that's the first main corollary I want to mention. Let me mention two kind of second-order ones. The first is that maybe you don't want a low-energy state. You want what's called a guiding state, which is a state that has a guaranteed overlap with that low-energy space, with the span of those low-energy eigenvectors. And this we can do if you're willing to fudge your precision estimate by just a touch, by an additive 1 over polynomial error. Okay? But I won't say more about that. Okay, this is a pretty straightforward consequence. The other one is that the runtime I told you is fully general. Okay, so it works for any Hamiltonian, but if you have specific types of Hamiltonians in mind, maybe you're thinking about 2 local Hamiltonians on 3 regular graphs, then you can improve that exponent by being more clever in how you design the algorithm. Okay, and I'll show you where this happens later. Good. So this is all I want to say about results. Let's get to proof technique. Right? So we're literally going to do exactly what this little girl is very happily doing in this picture, right? Which is we're going to cramp things down the toilet. And what do I mean by that? So I told you earlier that the local Hamiltonian problem on a 2D lattice is QMA complete, right? But it's not difficult to approximate it, okay, with an approximation algorithm. So here we have a lattice, right? And what you do is you take this 2D lattice, every vertex is a qubit, every edge is a constraint, and you break the lattice into constant-sized patches, like C by C patches. And what you do is you ignore all the constraints outside the patches, you solve locally in the patches, and you can do this because the patches are constant size. Okay? And then you just take the tensor product of all these local assignments. And you can show that for any epsilon, basically, as long as you choose your constant C big enough, this thing will give you a very good approximation to within the error bounds you see there. So, pros. This is actually a polytime algorithm. Okay, so this does much better than our algorithm in runtime. But the restriction is the fact that you have to deal with a planar interaction graph. And in our setting, we actually wanted to work for any interaction graph. We want to make no assumptions on the Hamiltonian. Okay, so we're going to trade runtime for generality. So how are we going to do this? The basic starting premise is exactly the same, right? I want to discard something, but now I'm going to focus on the vertices or the qubits, okay? Because my goal is to reduce the size of my system, okay, and then work on a smaller subsystem. So there's going to be a set of vertices R up here that I'm going to toss out, and there's going to be some remainder set of vertices R bar that I'm going to keep, and all the constraints that act solely in this R bar set, that's what I'm going to keep in my Hamiltonian. Okay, I'm going to throw everything else out. And now the obvious question, right? Which vertices do I discard? So the answer is, the most naive one, actually, right? Obviously, we want to discard those vertices that have the minimum overall strength acting on them, right? Because when I throw out those interactions, I'm going to minimally damage my Hamiltonian. At least this is what you would expect, okay? By the way, I said earlier that if you have specific types of Hamiltonians, you can get an improvement in the runtime, and this is exactly where you'd do it. You'd be more clever as to how you pick which vertices you're going to discard. Okay, so with that said, we've got 2 high-level steps. We're going to bound the loss incurred by restricting h to the qubits in this smaller space, and we're going to solve for the ground state energy on this smaller space. So let's start with the first. For a qubit v, we'll define the weight of this qubit as the sum of all the interaction terms acting on this qubit. Okay? And by hr bar over here, I just basically mean if I throw out all those qubits, this is my residual Hamiltonian acting on my residual space. This is what I'll call the baby Hamiltonian for the rest of this talk. And so what we're going to do is we'll order all these qubits by their weight. Okay, and my set R that I'm going to throw out, it's going to be the cheapest qubits in this sequence. And the question is, how many do I throw out? So we'll come to that answer in a second, like how many do we throw out? But let's suppose I throw out R of these. What's the loss in energy? Well, it's going to scale, like, from my original Hamiltonian versus the new one, versus the baby one, it's going to scale like the number of vertices I throw out times the weight of the worst vertex I throw out. Okay, intuitively, this is true. And then you can combine it with another easy-to-show set of inequalities on the weight of all the vertices that we're going to keep. Okay, and putting these together, you'll find that the loss in energy can be rigorously bounded by this inequality. So m times something. So in my mind, if I want a delta approximation, I can now set r to be something that scales like delta of n roughly. Okay, and then I'll get an additive error of delta m as I wanted. Okay, so this shows us that if I pick the size of the set of vertices I want to discard as something, I can bound the error I get in studying the baby Hamiltonian versus the big Hamiltonian. And now, once I can restrict my attention to this baby space, the question is, how do I come up with the ground state energy here? And so here, suppose I want to estimate the ground state energy to within plus or minus some epsilon m. I'm going to set my precision parameter to actually be slightly better than what I actually want. Right? I really want epsilon, but I'll set it to delta slightly smaller than epsilon. And then what I'll do is I'll run an off-the-shelf algorithm, say Lin and Tong. This is an algorithm based on the QSVT that takes a guiding state as input. And so in our case, we're working on a smaller subsystem, so we'll just give you the maximally mixed state. It's trivial. And we'll ask this algorithm to compute an estimate for the ground state energy of the baby Hamiltonian to within some higher precision than epsilon. And the runtime now matches what we get. Okay, and now I have this estimate for the baby Hamiltonian. When I go back to the big one, I'm going to incur another error. Okay, and that's why I wanted a higher precision estimate to begin with. Okay, so that when I get hit with that second error, I'll go back to the epsilon here. And that's it. Right? The idea is super simple. The speed up is just that we're able to bound the error in going to the baby Hamiltonian, and then we can just work on the smaller subsystem. Okay? Okay, the other thing is we talked about producing the low energy state. And how do we do this? So this is, again, going to be similar to Lin and Tong. We'll pick some precision parameter delta. We'll use our local Hamiltonian algorithm to compute an estimate of that baby Hamiltonian's ground state energy. Then, using the QSVT framework, we can probabilistically implement an approximate projector onto the low energy space of this Hamiltonian. Okay, of the baby Hamiltonian, let me be clear. Okay, so I can implement the projector. So what I do is I feed in the naive state, which is the maximally mixed state on this baby space. I apply this approximate projector, and then that gives me some state rho acting on this baby space. And our analysis shows that I can tack on whatever the hell I want on the set of qubits I threw out, and this whole thing will be a good low energy state for my original Hamiltonian. Let me mention just some quick detail. Okay. Why did I need to compute this low energy estimate in step 2 first? It's because if I want to implement this approximate projection operator, I need to know where's the cutoff in energy, right? So what do I consider low energy? Well, it's going to be that estimate I computed here. Everything below this will get, all the eigenvalues of my operator will get pushed to 1 approximately. Everything above this plus the error will get pushed down to 0, so I get an approximate projection onto this low energy space. Okay, good. So this was how we produce the low energy state. Finally, let me tell you about this corollary we had about the existence of exponentially many low energy states. This will follow very naturally now from the previous slide. Okay, so again, we can do the same thing. I'll just focus on this baby Hamiltonian. I'll compute the ground state of that. Imagine I have that at psi. And I threw out R vertices, and what we saw on the previous slide was that I can put whatever I want on those R vertices and come up with an assignment, X tensor psi, and that will be low energy by our analysis. Okay? And so now, since I have complete freedom on R qubits, I can construct 2 to the R orthogonal states, of course, right? And all of them will be low energy against the full Hamiltonian. Okay, so this tells me that there's a subspace of exponential size that is low energy against the Hamiltonian. This is not quite enough to argue that the Hamiltonian itself has that many eigenvalues. That's a different story below that cutoff. Okay? To make this fully formal, you have to apply something like the min-max theorem, and then this will really tell us that below this threshold, the original Hamiltonian H really has this many eigenvalues. Okay? Okay, that's it. Again, very simple. Good. So that brings me to the end of the talk. Let me give you a summary and some open questions. Okay, so we talked about the fact that we can approximate the ground state energy of arbitrary local H in sub-Grover time, and I put this again in quotes because we don't really beat Grover, right? There's actually hidden structure here in this problem. Okay, and the structure is that every local Hamiltonian has a low energy space of exponential dimension. So open questions. I talked a bit about these ETH, these exponential time hypotheses that are like no-go theorems that people strongly believe. In this work, we posit something called the quantum gap ETH, which more or less says that you can't beat our algorithm substantially if you really want a general algorithm that works for any precision epsilon. Okay, so there exists some epsilon and some constant c so that you cannot solve, say, 3-sat, which of course also means 3 local Hamiltonians, to within this error in this time. Okay, so this is just a hypothesis, of course. We just stated it, so whether it holds or not is completely up in the air. The constant we get is this funny thing over here. This is our value of c that we get in our algorithm. And the questions we can ask, of course, are, well, first of all, we have no idea what the best c is. Right? So can you get a better value of c that works for any epsilon? Okay, number one. Number two is that I can do this the other way, right? I can first say, okay, I want to fix some epsilon that I care about. And now for that, I want to come up with the best c. And here, of course, if I pick epsilon to be really, really large, so I'm allowed to make giant error, then I can even solve this in polytime, right? I mean, this becomes trivial. So certainly then you expect to get better c's and even sub-exponential time in some cases. Okay, and finally, the notion of this exponential time hypotheses has proven very influential over the last 20 years in an area called fine-grained complexity, where you're trying to show lower bounds on polytime algorithms to say that there's no better polynomial runtime for this algorithm. And so you might ask, what are the applications of a quantum gap ETH? There's already been some work, for example, for quantum ETH, but this gap version is new, so the question is whether there's anything one can say here. Good, so that is all I have for you guys. Thank you very much for your attention.
Thank you very much for the wonderful talk. Is there any question from the audience? Also, the second speaker, please come to the back of the podium and get things set up. Is there any question? Please.
Yes, so thanks for wonderful results and wonderful talk. I was wondering, so you mentioned that even Grover beats Grover. Can you say a little bit about whether and by how much your algorithm beats the Grover that beats Grover?
If I'm not mistaken, I don't know if we actually worked out the exact difference, but it's not a big deal. It's a very small improvement, if I remember correctly. So it's not like it's something substantial, right? So this is why I say that this observation that there's a large dimensional Lorentz subspace, this is kind of, to me, one of the more interesting parts of the work, frankly. Right? Sorry? Yeah. Well, the question was, it took your work to show it, and yeah, I'm glad you see it that way. Yes.
Can I? Yeah. So the result doesn't say anything about the degeneracy of the ground subspace, right?
No.
Yeah.
No, absolutely not. Because then you're getting into like Sharpie-Hart problems, right? Then you're counting things like a solution space dimension, and presumably, I mean, in general, this is going to be hard, right? So that's even harder than solving for ground state energies.
But then it's still a generic fact that as soon as I'm epsilon above the ground state, I would have an exponential degeneracy.
This is the main, I think, result of the work, I would say, yes. That comes
Interesting.
out. And it also gives you new classical algorithms in that way.
Hi, when you use QSVT to implement this approximate projection for the state preparation, do you need a promise on the gap between the lower slice?
That's a very good question. So if you want, so here's the thing. If you want to resolve things about the ground space itself, yes, you need a spectral gap. And so if you look at Lin and Tong's paper, indeed, they need that spectral gap assumption. But we're dealing with just Lorentz space. I don't exactly care which eigenvectors your support is on. I don't even need you to be in that space technically. So then you don't need the gap anymore. And there's a section 6 in Lin and Tong's paper that does something very similar, frankly.
Okay, thanks.
Yeah.
Okay, given the time, we will not take another question. Please consider to talk to the speaker afterwards.